So here's this first example of shear wall design. So in this example, we are asked to check the adequateness of the thickness given to carry an amount of 240 kip load. That means, firstly, we need to calculate the shear capacity or the lateral load capacity of this shear wall using the geometry and using this formula, and then from the capacity we need to conclude that whether this wall can carry this 240 kip load or not. So this is the actually the capacity checking problem. So let's see the example. In this example, a shear wall shown in this figure is intend to carry a shear force of Vu is equals to 240 kip. Find whether its thickness is adequate to carry the force, given that the compressive strength of concrete is equals to 3000 psi and yield strength of steel is equals to 60,000 psi. So the necessary information and the geometry is given. So we need to calculate the capacity first. So using this formula where 5Vn is equals to 5Vn is the capacity, or it is also indicated by Vu, same thing. So 5Vn is equals to 510 root over Fc prime B into D. Here B is the thickness, which is given as 8 inch, and D is the effective length or effective depth of cantilever beam. As I have mentioned earlier, that if I just rotate this orientation in clockwise, that means we know that the shear walls are fixed here in the from downward, and it's being continued to the topmost portion. So if we rotate this orientation in clockwise, so we can say that it's connected to the foundation, and this is our shear wall where load are being imposed from this portion. So this is the height, which is HW. This is HW, and so it's simply a cantilever beam. It looks like a cantilever beam. So if we consider it as a cantilever beam, then this is the total depth, and from total depth we can easily calculate the effective depth, which is 80% of total depth, or 0.8 LW. So it is actually, we know that we use reinforcement in shear walls. So from the center of reinforcement and to the end, the distance from the center of reinforcement layer and one end is known as effective depth or effective length of shear wall. So we can calculate D using D is equals to 80% of LW. So from here we are calculating the value of D in inch. Now plugging the value of D in this capacity equation, we are getting the value of 5Vn, or design capacity of this shear wall. That means this shear wall will be able to carry a lateral load of 315.5 kip in total. So we can see from the question or from the figure that a load that is being imposed is 240 kip. So this wall has a capacity of 315.5, but load being imposed is 240 kip, so it will be able to carry the load. So in this way we'll have to conclude that as the design capacity is greater than the imposed load, so the thickness is adequate. So if it wasn't adequate, then we need to change the section, whether we need to increase the thickness of the shear wall, or we may also increase the length to some extent. So in this way we can increase the capacity also. So this was our first example. In second example, we are told to design the vertical flexural reinforcing That means we need to design the flexural reinforcements which are generally used in tension phases. That means if a load being imposed from this direction, so tension will develop here. So how many vertical reinforcement, flexural reinforcement we need to use, or we need to use in our design? Now we need to calculate from the using in this problem. So design the vertical flexural reinforcing of the shear wall shown in figure if Fc prime is equals to 3000 psi and Fy is equals to 60,000 psi. So we can see here the shear load or shear force 240 kip is being imposed, and total height is 14 feet. The length is given as 10 feet and the thickness is given as 8 inch. So firstly, from this geometry and from this question, using these informations, we need to calculate the amount of shear reinforcements. So as we know that we have also mentioned earlier, shear wall acts as a vertical cantilever beam, as a deep cantilever beam. So in order to design cantilever beam, we need to use the design of beams formula, so which we have known or which we have learned in our previous semester, that means in structure 5. So using the same formula of cantilever beam or the design of beam process, we need to calculate or design this shear wall, design the flexural reinforcement of this shear wall. So in this case, we know that in order to calculate the amount of reinforcements, we need to calculate the area of the steel firstly, and from the area of steel we used to calculate the total number of bars. So in order to calculate the amount of steel, which is AS, which is denoted by AS, we need to know the reinforcement ratio, which is rho, and gross cross-sectional area. That means the cross-sectional area of this section. So we can see here that this is the width or thickness B, and this is B, and this is the LW. So our gross cross-sectional would be B into LW, but as we are taking the effective depth or effective length, so we are taking the 80% of this length, which is indicated or denoted by D. So our gross cross-sectional area would be, in this case, B into D. So here we can see BD, which is our gross cross-sectional area, and in order to calculate the amount of steel or reinforcement, we need to know the steel ratio rho and also the cross-sectional area. From the geometry we can easily calculate the cross-sectional area, but we need to calculate the rho first to calculate the amount of steel. So to calculate the rho or reinforcement ratio or steel ratio, we need to use this formula. So this is the formula where we can see 0.85 Fc prime by Fy. This Fc prime and Fy's value are given in the information in the question. So into 1 minus root over 1 minus 2 into Rn divided by 0.85 Fc prime. Here Rn is the nominal flexural resistance factor, and Fc prime, we know the value of Fc prime obviously. So to calculate the value of Rn, we need to use this formula. This is exactly the same formula that we have used in structure 5 to design the beam. So we are using the same formula of beam. So in that case, we need to use the value of reduction factor phi as 0.9, because for beam the value of reduction factor is 0.9. So we are using it, the value 0.9. It will be fixed. It will be used as fixed value, and mu is simply the ultimate moment that is being imposed on this structure. B is the thickness, and D is the effective length or effective depth. So firstly, we know that D is 80% of total depth or total length. So the length is given as 10 feet, so 80% will be 8 feet. 8 feet means 8 into 12, which is 96 inch. So we are plugging here 96 inch, and for B, which is the thickness, it's given 8 inch. So we are plugging the value of B. Then mu, moment. So we know that the shear wall is fixed in this portion. So if we see this figure, which is a cantilever beam, so if a load is being imposed from here and it is fixed on this portion, so the total moment will be force into this length or this height, which is denoted by HW. So in this case, you can see the load imposed is 240 kip and the distance is HW is 14 feet as it's being fixed from this portion. So moment force into distance will be our moment. So by multiplying force into this force with distance, we will get the value of moment in feet. But as we are plugging the values in inch, we are converting it to inch, multiplying with 12. So plugging the value of moment, we will get the value of Rn, and plugging the value of Rn, we will get the value of reinforcement ratio, rho. So we are getting the value of reinforcement ratio, and from reinforcement ratio we will get the value of, or get the total area of steel required for flexural reinforcement, required as flexural reinforcements. So as flexural reinforcements, as we are asked to calculate the flexural reinforcing, so for flexural reinforcing we need to use total area of steel of 9.03 inches square. So now we need to calculate the amount of bar required. Suppose we are using here number 9 bar. We know the area of number 9 bar. The bar chart is given in your previous lecture in column section, in reinforced column. So from there we can take the area of individual bars. So for number 9, we know the area of number 9 bar is 1 inch square. So if we are going to use number 9 bar, we need to use 9 number 9 bars, that means 9 inch square. No, it doesn't meet the requirement. But if we use 10 number 9 bars, that means 10 into 1, which is 10 inch square, then it meets our requirement. But in that case we need to do higher rounding. So we are using here 10 number 9 bars and getting the area of steel, using the area of steel as 10 inch square. So we are using 10 number 9 bars in total. Now we need to plug it in our figure, drawing a figure as this cross section. So drawing this cross section, we need to show 10 number 9 bars. That means this is 1 bar, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. So as the load is being imposed from this direction, so we are using this in this phase. So these are our vertical flexural reinforcements. So we need to level it as 10 number 9 vertical flexural bars. So we are not confirmed that whether the load is coming from this direction or from this direction. So assuming the load may come from either direction, also assuming that VU could come from either direction, so we are using the same amount of bar in this phase also. So we are using 10 number 9 bars in this phase also. So in this way we will show in the figure that 2 layers, 5 in each layer, in both phases, 10 number 9 vertical flexural bars, and conclude our design for flexural reinforcing.